Halo. Halo.
Yuk, tes.
Yuk. Halo Mas Radhian. Halo, Mas Radhian. Kedengeran nggak?
Halo.
Halo. Kedengeran nggak?
Yap.
Sip. Sorry, kamu nungguin tadi kayaknya.
Oh iya, nggak apa-apa.
Iya. Biasanya Zoom tuh ada alternatif hostnya gitu, makanya aku kayak kalau misalnya aku tiba-tiba kayak tadi pada nggak kayak belum itu, aku sama anak-anak lagi coba mau nge-streaming kayak YouTube ke YouTube gitu presentasi kamu, kita kayak excited banget kan.
Oh iya.
Lagi kali. Iya. Jadi Mas Adit ini kayak partnerku bareng-bareng di Bitwyre, dia CEO kita.
Ya, Mas Radhian.
Halo Mas Adit. Halo.
Kita kayak aku cerita pas terakhir kali ketemu kamu itu di Pasfest. Terus kayak kita kayak paper gitu, terus kayak scribble terus gitu. Iya. Masih kamu tuh ini oke, sip. Saat itu aku Telegram 6.15 ya, ntar lagi.
Oh, ada Radhian.
Oke.
Ada Hasani. Wah.
Halo Hasani.
Halo.
Hi man, how's it going? Hey. Hasani, do you hear me well, man? Oh, he seems to be muted, or not. I don't know. So yeah, let's. Okay, so I guess let's wait for a couple of minutes. I'll just like blast this to the several others. So okay, mau pakai bahasa Indonesia, pakai bahasa Inggris nih?
Bisa dulu kali ya?
Bisa dulu.
Pesertanya. Kalau pesertanya orang Indonesia, mau pakai Indo aja.
Recorded. Tapi recorded kan? Nanti temanku juga mau lihat.
Oke.
Recorded nanti.
Sip.
Oke.
Cool. Iya. Jadi Mas Radhian ini sekarang kerja di Monad. Maybe kamu introduce.
Oke. Ya, halo semua.
Halo.
Ya, halo. Ya, saya Radhian. Bekerja di Monad, cryptocurrency mining hardware venture backed by FPGA. Sekarang company-nya ada dua sebenarnya, dua base, ada satu di Taipei, satu di Jakarta. Aku yang di Jakarta. Gitu. Jadi mostly bikin hardware buat cryptocurrency mining dengan basis FPGA gitu. Kemarin waktu ketemu sama Mas Dendi, kita ngobrol-ngobrol sedikit tentang FPGA. Sebenarnya aku juga bukan yang senior developer yang gimana, aku juga baru lulus 2018, lulus S2 2018. Jadi saya masih newbie juga. Gitu.
Cool. S2-nya kemarin spesifiknya tentang FPGA apa? Research.
Iya, sebenarnya IC design. Iya, IC design. Jadi
terkenal banget di UK, ada perusahaan chip namanya Graphcore gitu. Kayak lagi banget sekarang.
Iya. Ya, Graphcore, ARM juga dari
sana
ya. Iya, ARM dari UK. Gitu.
Iya. Jadi kayak buat anak-anak yang so kayak buat maybe if you guys are tuning from wherever you are in the world right now, this will be recorded later on and will be provided to our YouTube channel.
All right.
So also we try to stream it to like Periscope, but like and also YouTube. I think like we failed. We might try it next time. I think it was like the fourth time we did this. So we try to use hexadecimal, right? So OXOO, OXO1, OX now it's OXO3. Like the first one was like started like maybe like the 3-4 months ago, right? So it was the first one was Odie, explaining about JavaScript and TypeScript and React, and the second one was about Kresna sharing about his like Rust matching engine implementation, which was in the more order of magnitude of above like 1 million orders per second, which was really cool. And then who's the third one? I forgot. Last week it was. Do you remember Preston or? No, I think. Anyways, so this conference is about low latency or like low level systems in computing, and thankfully today Radhian has like agreed to give a presentation on FPGAs and basically FPGAs in crypto mining and FPGAs in general. And yeah, I guess I'll leave the floor to you, Radhian.
All right. Hello all, hello everybody. Yeah, thanks for everyone for coming here, and also thanks for Mas Dendi for inviting me. So I'm also excited to sharing a bit of my knowledge and my design experience using FPGA from from in the company, and also from my undergrad and master study, and also my research.
Sure.
So I think I will just share my slide. Okay.
Sure.
Share. Wait. Here, can you see my slide?
Yes, we can see it, right?
Okay. So wait.
Wow.
Okay. So here. So this is about more introduction. So because I think most of the audience will be a software developer, and FPGA is more like for IC design people and also for electronic people. So I will more put on weight on the introduction of the FPGA, and also to make it more interesting. So I will talk about also about the application in crypto mining.
Cool.
So actually, I have used FPGA since 2012. So yeah, 2012, 2013 actually, when I was an undergrad. So I studied digital system design, and my professors like do the uh, uh, experiments, like implement your design in FPGA, because it's more hands-on project. It's more practical, and it's more industry oriented. So after that, I'm fascinated to do my digital design in FPGA, so on and so forth, until I did my research on there. I did my master, and also I work in the FPGA stuff. So this one. So in this presentation, uh, I will talk about the FPGA mostly, about 70% about what FPGA is and the architecture, and also how we design briefly and how do we program that. And at last, I will explain a bit about the cryptocurrency mining with FPGA. So in these ones, actually, I prefer to have a deep question at the end. But if something unclear in the middle, please just interrupt me.
Okay.
Yeah. Okay.
Sure.
Got it. So why FPGA matters? So actually, why FPGA? So remember, in the conventional or traditional computer board, we have CPU, we have I/O, and a flat SDRAM DSP module, and something like that. And if you remember your laptop, right, it has a Core i7 and on the GPU in there, and something like that. But for the performance wise, like this kind of computers kind of have a high latency. It actually depends on the application, but for the high performance application, the it kind of have a high latency and high power, and also the limited connectivity. You can, you know, right, in your, like in MacBook, yeah, like the connectivity is only, yeah, something like that. You know what I mean? And yeah, and so we can make our kind of reconfigurable computers using FPGA, field programmable gate array. So we can make put the DSP module in there, or CPU, or we can also make the custom GPU, and also we can make the custom IO. Like IO means like USB, SBI, UART, GPIO, and stuff like that. So we can eventually we can evaluate our design to the FPGA, which means we can reduce more area and more energy efficiency and less latency and something like that. So in brief, we have like disadvantages and advantages of FPGAs. So because in our computer systems like CPU, so it's that instruction based, right? When we write the code, like for example C code, and it will go with the compiler will convert that into the assembly language, and eventually the assembly language will turn into the binary, and it goes into the processors. Several instruction here that may latency become high. But with FPGA, we can make that more straightforward. We just compute, we just make the things that we just want to compute, right? So we can improve the latency significantly. Okay, and also for the connectivity. So you know the typical computers that has a limited and dedicated IOs, but in FPGAs we can reconfigure our IOs itself, like with the specific application with specific specific function. And also for the power efficiency, because we just compute the things that we want to compute, and depends on the application, but mostly for the low for the power efficiency stuff, it's advantage compared to GPU or CPU for most of the cases, but depending on it. But unfortunately for engineering costs, it's not like just, it's not as versatile or as adaptive or as flexible as the software. So yeah, so the engineering cost will be higher, and also you know the FPGA units is very expensive. If you know like a full-text ultra scale that we normally put in data centers, it can cost $3,000, right? Something like that.
Can I ask a question, Radhian?
Yep.
So you said previously that there's some stuff that is not run on, like it's not like the CPU. Maybe for our viewers later on, why does the FPGA, like you mentioned about, it runs only the stuff that you configure it to run, and not like anything else. So does it mean that our CPU runs different kind of algorithms while you also run the algorithm that you intended to run, or how do you?
Oh, are you saying like how the FPGA performance is like against when
Exactly.
oh yeah, so actually I will explain later on.
Okay.
Yeah.
Okay. Sorry about
Yeah, that's okay, so this one, so actually FPGA is found in various industry. In brief, if you need a high performance system and you like you want to instead of having the dedicated electronic circuit, I mean dedicated electronic circuit is very high speed, right? But it's not reconfigurable. You want high speed, but you also want to reconfigurable. So FPGA solution. Like for example, in the automotive, when you have camera and navigation system for self-driving car, automatically you need a high performance in your car. So FPGA can be a great choice. And for the medical like MRI, or also a lot of image reconstruction, image processing for the for detecting cancer and stuff. It also needs a CPU extensive and memory extensive. So FPGA also can be a solution. Of course, for the computer storage, for AI inference hardware, security, data centers, and also in aviation and communication, and also for in the finance and cryptocurrency for high frequency trading, finance modeling, and crypto mining.
Yes.
Okay, so actually this one is I got from Intel. So from 1986 to 2020. So on the left side, we know the transistor performance, like the Moore's law, like the Moore's law said, like the transistor the density will be double every year. But actually, because in the modern system, we able to do more parallelism. So the transistor we don't need to I mean sorry well with the current system it's very hard to make the density of transistor become double. It's because like there are the physics constraint in there. So a lot of innovation comes to do more parallelism so that we can make a more higher throughput system and lower latency system. Yeah. And this one. So the system that we built right now has three bottlenecks. So first is CPU intensive. So and the second is memory intensive, and the third one is I/O intensive. So first for CPU intensive, uh, CPU intensive normally if we want to compute like routing and also like financial modeling and something that we need a lot of iterative method or something like that, it needs for CPU to compute with a very high performance, and it requires a higher power. So in the chip, so the power actually happen when the transistor becomes 1 or 0 to 1. When it happens, it costs a lot of power. Costs power, and if that happens very frequently, so it takes a lot of power from the CPU. So if we do a lot of like multiplication and iterative function a lot, so the CPU expensive becomes higher or something like that. And also memory intensive. So this one, if you know, like Ethereum mining, we normally use HBM because a lot of caching and parsing. That's make the system becomes memory expensive. So normally we design the system using the hierarchy of memory, right? Like the SRAM is or case is like nearby the memory, and like HDD SSD will be longer than the CPU because because it's like cost issue. Like if everything is SRAM, it's not effective, it's very costly. We want the chip system, so we need to high speed and also reliable. So we need to compensate all of those. So eventually we can find a memory intensive. For memory intensive application, it will slow down the performance. And also the I/O intensive. Like I/O intensive, normally if it's just using a limited transceiver, like for example USB or UART or something like that, it's it's low cost, but it's very limited. All right, but for different application, we need more high-speed transceiver like PCIe, right, or Ethernet. So we can reconfigurable that using FPGA. So these three bottlenecks becomes a challenge to build a the system become high performance.
I see.
So yeah, need to think about the compute offload. Okay, so in the future, solid state computing, I don't talk about the quantum computing. It's solid state computing is transistor based computing. So we eventually will merge the CPU, GPU, the FPGA into one system, something like that. Or like in the current system, like in the mobile phone or like the normal, or people make a system on chip, is normally have the FPGA and also Linux core in there. So we that can try the master method. So the Linux will do all the communication stuff with the website with the become the middleware basically and communication through the API. And for the like cryptography, security, and decoding and communication that needs a lot of fast uh, fast and low latency performance with the FPGA in there. So like the communication between both becomes more efficient.
That is true. That is so true.
Yeah, so like here I put the application for modern system like control intensive, data intensive, and compute intensive that I already talked before.
Yes.
So we go with the architecture. So what the elements that create the FPGA? So here on the right side, you can see the FPGA is consists of logic elements, right? So we know FPGA stands for field programmable gate array. So gate array is actually the gate is refers to logic element. See, so logic elements or CLB, configurable logic element, this is simplified. In the modern system, like the Xilinx or Altera products, that's the biggest supplier of the FPGAs right now. It's not like this. This one is just simplified to make more understandable. So it consists of LUT or lookup table and register, or in the electronics theory, we call it a D flip-flop registers. So LUT or lookup table, uh, we can convert that into the several logic what is that? A logic element. For example, AND gate, OR gate, or something like that. So we configure, for example, the bit stream. When we program the FPGA, when we synthesize it will turn to the bit stream. The bit stream this lookup table, so it behave as the way we want. For example, oh, I want to make the AND gate like or 1 and 1 equals to 1, 1 and 0, yeah, for example. So we program so we make the bit stream. So our code becomes the bit stream, and it program the LUT, and it becomes the AND gate, and our input that output will follow that AND gate. So something like that. That's a simplified version.
I see.
So sorry, here. So inside the tiny, so this is a micro scale of the FPGA. So if you take a look at that, so this logic element has several, this cell, the red cell has a element of the LUT, or for example, like that. Okay. And in the LUT, this is the modern, so this is Intel Altera FPGA. So they have a LUT and carry logic. So carry logic basically like like the controller, and also the registers. The registers is a simple memory. So like if the data comes out from the logic gate, then we need to store first. After the next clock cycle, so the data will pass through this register to the next cycle, to the next step. Yeah, something like that. So registers just a simple memory. And other than that, so FPGA also has the I/O elements. Like the I/O, we can connect USB, SPI, UART, SPIE from the I/O elements. We can put the pull-up resistor in there, and also we can do the differential signaling. And also we have the embedded memory in there, so we don't need to use the register all the time because, for example, we have like the resources, right? And normally the register is we prioritize for the high speed application, for the high speed storing, for the but for the next level of memory, so we use the embedded RAM or embedded RAM in there. So, and also we use the DSP blocks, right? Actually, in the digital system, we can make our own adder and multiplier. But if we make that on FPGA, normally it takes time. It takes a lot of latency. So normally we just use the DSP blocks in there. It's the performance is great already. So
could I ask you a question, Radhian?
yeah, yep.
Yeah. So you said there on the I/O elements as input, output, and bidirectional. My question is, do you bidirectional? I mean, so you could have another system that connects to the FPGA. Is it a push or a pull thing, or the FPGA could do both, or?
Yeah, FPGA can be pulsed.
Oh, could do both. Okay.
Yep. Great. Okay, and also there are a clock structure, and we have the like a crystal in there. and also it had a VCO, voltage control oscillator, that we can control the speed of the oscillation, the clock, using the voltage. It's embedded in there, and also PLL and DLL.
Okay. Okay.
Okay, and we do for the design and programming process here. So the design idea, of course, when we want to make the something, so we go with the design idea. So normally the things that we want when we choose FPGA is a good thing. So the first thing that you must think your application. You need a very high speed, you need a lot of resources, and do you need power efficiency and something like that. Does your CPU or GPU cannot do that to reach that specific kind of latency? Like for example, for my application like crypto mining, right? So because GPU and CPU will translate that into the instruction for the assembler, compiler the assembler into the instruction, and there is no one instruction takes a lot of clock cycle. But here, I can do one hashing, one clock, for example, like that.
You could do one hashing in one clock.
Yeah, one hashing and one clock, right?
Wow.
One hashing, yeah, one hashing and one. Yeah,
Could-
so depends
could
on
you-
the application.
Right. Could you explain a bit to maybe to the viewers who might don't have like a bit of computer science knowledge? So what do you mean by one clock, and what do you mean by so explain a bit maybe about your crypto
Okay.
cryptocurrency mining, yeah.
Yeah. Okay. Here. Uh, for example, okay, I make a new cryptography algorithm.
Okay.
The cryptography algorithm, it just AND gate.
Okay.
It's just an AND gate. Okay, if I make an AND gate, right, and I compile that in C, for example, so the instruction, right, the instruction will be A and B, but in your computer system, so when you put that instruction into the CPU, it will go through a several cycle. You know, the CPU has like fetch, instruction fetch, and so also operation and something like that. It takes 4 cycle to get the final output.
I see.
Yeah, but for FPGA, because we make just AND gate, just AND gate, just AND gate, so it can be simultaneous, but the AND gate itself has the latency, right? Even though the latency is really low, but it has latency, so we can push the clock cycle until that latency.
Okay.
Yeah, something like that.
Yeah, that's
Yeah,
amazing.
yeah. So that's a comparison to the CPU and the. Actually, I will have. So there are code comparison later on.
Wow. Okay,
Yeah.
that's really cool. Can't wait.
So here, so we need to think the specification, like when we literally need the FPGA, when we don't need FPGA. Of course, the algorithm that IO, do we need the what algorithm that we want to implement, and what IO, and also bandwidth, latency, and speed, and data path, and something like that. After we do the design, like we do the design code. The design code is a bit different. Actually, it's different. It's different than the software, because we use the register transfer logic and gate programming. Before that, we use the higher levels abstraction language with the behavioral programming. That's the things that we usually understand in software layer. That so the like a sequential things. So the program will go through from the up to bottom, something like that. If the multi-threading happens, so it just yeah, the multi-thread. Yeah, but normally like that. But for this one, behavioral programming is something like that. But we later on we move to register transfer. It's totally different, and all the things we call as a hardware description language. So in brief, we make those logic language, those logic gate, registers, multiplier, and stuff into the code. So it's not like software. Software is normally we make the instruction, right, and the compiler will turns that into the assembly code. Assembly code into turns the instruction binary, and inside the binary go to CPU and stuff. So it's not like that. So we translate that into the circuit. So it's yeah. So that's why we call that a hardware description language. After that, we tell the tools that we use, either Xilinx or Altera, both of them have a different tools, to put our hardware description language, right, into the FPGA. So it's called map, routing, and place, or synthesis. The tools will think, oh, I need to put this logic gate in here and here, here, here. So the tools can think by itself, but also we can do manually. So it's depend on your perspective. So everything has a trade-off. So after that, those we turn all of them into the bit stream, because that bit stream eventually we need to program that into the EPROM in the FPGA. So the EPROM can program the LUT to be something that we want. Yeah, something like this. So like X9889 is the output, one of the outputs of the bit stream. Yeah, so that's the process. But actually, this is ideal scenario if nothing happened. If like, oh, no bug at all, but it never happened, right? So in the middle, we have simulation. Normally, we in software level we compile things, right, and we build, and we make using the Makefile and stuff. And after that, we use the IO and see the IO and stuff. But here, we need to do simulation. So different term. So in the simulation, we normally give the input test factor, and we know the output. I mean, we know the expectation. For example, if we for AND gate we give 1 and 0, the output will be 0 or something like that. And function. So we do the functional simulation. So functional simulation means, so as I told before, each gate has delay, right? So when I put the data, so it has a delay at the end, even though it's at the scale of nanosecond, but it's still delay. For the larger system, it will matter so much. But so functional simulation, it just normally just functional. 1 and 0 is equal to 0 without any delay. But when we do synthesis and place and route, we actually implement that into the FPGA. So FPGA has a different technology. There are 22 nanometers, 28 nanometers. Everything has a different delay for each logic elements. And also how we route the block logic elements in the FPGA will matters to the latency. So we do the iteration in the timing simulation until it doesn't corrupt it, until it gets the result that we want. After that, actually, when the timing simulation, if it's good, normally when we program the bit stream, we flash the FPGA, like 95% of the what's that? 90% of the implementation will be successful. Yeah, so 95% chance if it pass the timing simulation, it will be successful in the real board implementation. Yeah. Okay, design code. So we use the hardware description language, right? So that's a language used for describing a digital system or digital circuit. It's not a programming language, so we turn that into the code into the digital system circuit. So, and commonly there are two things. There are two languages that very powerful for HDL. First of all is Verilog, and second one is FVHDL. And actually, like in brief, the difference is follow. So VHDL normally for debugging process, for system debugging process, is more robust. But if we want to go through more detail into gate process, into like we need to observe the gate delay and stuff, Verilog is better. So actually for myself, I'm more comfortable with Verilog because like years of development, I use Verilog. Here's the design code example. So this is the AND gate that I told you before. So in the left side, it is AND process in C, right? So in AND test, input A and C and return A and B. Very straightforward, very simple. And as I told before, this one will turn into by compiler, we turn the assembly language, and assembly language by assembler will turn into the instruction set. So, but when we put that into the instruction set, it takes several cycles to get the output, right? Because there are many stages in the CPU that happen. But On the other hand, when we make the Verilog like that, so we use the module. So module means it's not like function. Module means, well, there is a digital circuit that we make. So we need to declare what is the IO, like on the top, like result and test in A, in B. Different in here. So the data structure, right? The data structure in C is very high level. Like we know what is in, we know what is in, we know what is floating point, we know. But in here, it's literally like bit. So we need to declare that like input 15 to 0. It means 16 bit in A and in B, something like that.
Okay.
So literally like gate level 110.
Okay, so question for me. So
Yeah.
it's kind of weird from a C++ programmer in my stance to see inputs and 15 to 0. So you say you read it from like the 0th bit to the 16th,
Yep.
15th bit?
Yeah. So it's like 16 U integer.
Right. So
Yeah. So it's
if
like,
you want to put like, for example, UN64T, for example, it would be 63 to 0, correct me if I'm wrong? Or
yeah, yeah,
something like that. I see.
yeah, something like that, like bitwise add.
I
Yeah,
see.
yep,
Mhm.
yeah. So the data structure is very, very low level, you know. Yeah,
I
so
need
like,
to comment something.
Right, right. Go ahead, Tessa.
Uh, yeah, I was muted, but I was laughing when Radhian said C is very high level.
Yeah,
oh yeah,
we laugh because like,
yeah, I know,
C
I know.
is very high level. Oh my
Yeah,
god.
right,
yeah.
right,
In terms
right.
of the CPU, in terms of the Verilog, yeah, C is high level.
Yeah,
C is high
exactly.
level.
Okay.
It's hilarious because like here, like so
Yeah.
so Bitwyre, maybe like Kristen Suseno in the F2,
Yeah, I
and
know.
and Augie works heavily with either Python or C++ or Rust, which is already pretty low level to a lot of people.
Yeah. I
So
know.
yeah,
I understand.
it's
Yeah.
very,
Saya
Now,
Python is high level.
yeah.
yeah.
Now I can say that Rust is a system language, but it's not low level enough.
Yeah,
Low level.
agree. It's a
Once they
system
saw your
language.
presentation, yeah, man.
Yeah. Yeah. All right. Yeah. So moving on. This is the simulation that I'm talking about. So I just normally we just put the A with a like a clock, like a 101010, and put the B with a different frequency, so that we know the difference, the interception, right? Like this 1111010 or something like that. So okay. So simulation is successful. We can move to the synthesize process and so on and so forth. Here, so this one actually, let's actually I want to introduce about the pipeline. So pipeline actually in the what's that, in the C or the software language is not that famous, but in the FPGA developer, as a FPGA developer, it's very famous, and it's very fundamental theory that need to be learned.
Okay.
So pipeline is basically we put like, for example, we have the data and there is process and give the data out, and the output will go to the next stage, and the next stage will process the data and go to the data out, and so on and so forth. And we grab the last data from the last stage, or something like that. Like this one, I have the pipeline stage 1, stage 2, and stage 3. And stage 1 is just data plus 1, and stage 2 is we sum those output from data from the first pipeline, and also so this is just 2 times out 1, something like that. Or and pipeline 3 is just we do the OR, the XOR with 1, 2, 3, 4. So there's 3 stage. And first we do the 4 here, so it takes forever, and then we scan the data and goes to pipeline 1, 2, 3, and goes to out. So very straightforward also. But this one is very common in the digital circuit because we normally synchronize everything using clock. Right? So in here, like in C, so it's automatic below the void main. So it will sequentially execute the scanf pipeline, pipeline to pipeline 3, and vice versa. So it just, but in here, so we use clock. So inside the always, right? So I put a different always here, right? So always post edge clock, which means when the clock turns from low to high, so the process is happen. So when clock to high, so out one will store data in plus one, yeah, yeah, and also out two will store out one plus out one.
Okay.
Okay, and data out will store out two, and so it will be synchronous.
Okay.
So
So
yeah.
question
Wait.
on my part.
Okay. Please, then.
Does out one get destroyed every time on the pipeline, or is it still in memory?
Or still in the out one, but when the next post edge happen, so it will be replaced by the next data.
Out two. Okay.
Yeah,
So
yeah.
okay.
So this one, I mean, this process happen when the post edge clock happen, which means the clocks turns from 0 to 1.
Okay.
Yeah.
Wow.
I got a question.
Yep.
Can I say a clock is a cycle, like a CPU tick, like one tick?
Yeah. Like
Oh,
one tick.
Right.
okay.
Yeah, like a timer. Yeah, like a timer. So
So one tick, one process, one stage, right?
Yep. That's right. That's right. One state, one source. That's a pipeline. Now here, so the pipelining, why it matters in the design process. For example, if we take a look at the left side, so there are three modules: M1, M2, A1, right? So it's if I told you before, so one gate has a several like certain latency, right? So if we add those, so the latency becomes higher, right? So if we put the registers in the beginning, like in the next to A, I, B, I, C, I, and D, I, right? And I also put the register in YI, right? So we can push the clock frequency until only 200 megahertz. Otherwise, the data will be corrupted, right? That's a worst case because the delay will be 5 nanoseconds, which means there's 200 megahertz maximum. So should be less than that. However, when we do pipeline, so we isolate each stage with the registers, right? So the worst case delay for the clock is the worst case delay of the stage. For example, on the right, so because the worst case delay is A1, which is 2.5 nanoseconds, right? So each stage we can push until maximum 25 nanoseconds period, which is 500 megahertz. Yeah, but as the trade-off, we need to put extra registers in the beginning, at the end of the 8 cycles. When we put more registers, it consumes more LUT, more LUTs. Yeah, it's something like that. So yeah, so there's a trade-off between latency when you design the FPGA. Here, this is the CPI architecture that I told you. For example, when we do the end, what is that? The pipeline process.
Right.
The pipeline process, right? So it's so for example here, and this is the CPU, right? So like one end gate, just from here, go instruct that and do the operation and put the output here. It's already several cycles just for one end. If we want to do several steps of end process, so it takes a lot of time, right? So but for here, so we can this load means the cycle, the web cycle. So this one, we put the register, this is register, and we pipeline each process. There's another process in there, and there's another process in there. This should be actually there are, oh yeah, this is register, yeah, right. And register in there. So we can isolate each process with the flip-flop so that we can achieve higher speed and low latency. and also the resource become lower too, because for example, if we just want to make an array of AND gate instead of using CPU, because it has many things that we don't need to compute the AND gate, but FPGA is a good choice because the array we can make the computer just to have the AND gate. So, yeah.
Wow. Okay.
Here. Oh, the next step we go is the functional simulation. After we get what we want, we synthesize. So synthesize is actually is more hardware design, because when we synthesize, it's specifically targeted which hardware that we use, because each hardware have a different technology. If different technology means different different latency, like the gate will have different latency, also different power consumption. Like normally a lower gate, like 22 nanometers, has more, it's more power efficient than 28 nanometers or something like that. And when we map plat and root, normally that's more like we need to think how to take the resource as efficient as possible and vice versa. But actually, if you don't really care about the power, area consumption, actually all the tools that Xilinx and Altera have already have the synthesizers. So the tools will think by itself, like, oh, I need to put the logic here, I need to put the AND gate here, or this process here, and so on, vice versa. Like the one on the right, it's using the Intel FPGA. So it's color different models. And yeah, but when we concern, like for example, like my application for crypto mining, we need to push the cryptography algorithm in there. We want as fast as possible, and we need to put a lot of cores in there. So this resource is matters. So we need to do another optimization layer. So we call it partial reconfiguration.
Right.
So partial reconfiguration normally actually, so this one, we just let the tools like, okay, root by yourself, like, and he just do like, like make a messy, messy routing, right? But this one we can like target it. Oh, for this core, I want to just utilize this area, for example.
Okay.
This area below here. So it's more organized, it's more efficient.
So somewhat it's an optimization process.
Yeah, there's an optimization process.
Okay.
So yeah, something like that. So this is, I think, briefly for introduction for the design process and for my application. So here, actually, I just told you like briefly because most of them are company confidential. So
Sure.
So first thing first. So we so there's many mining coins that are very profitable at the like a couple years ago, but there are 2018 there are market crash because actually there are several companies that build ASIC mining, right? ASIC mining, which integrated circuit that dedicated for mining, that it make the market becomes like broke the market really hard, and
it was Bitmain, right? There was
Bitmain. That's right, Bitmain.
Yeah, Bitmain. Okay.
Yeah.
So,
but yeah.
So
okay.
there was a phenomenon lately about increasing hash rates, even though there has been a market crash. Is it somehow related to anything or not so ever? Do you have any hypothesis on yourself? Or?
Oh, actually, for now, for the FPGA is we targeted a small coin, so we never beat the ASICs for like Bitcoin or Ethereum. Yeah, so we targeted a small coin. Okay. So for example, everything starts from Wildfire's Bitcoin Talk article. So they made a prototype using the what was the data centers FPGAs, and it runs the AWS. And it gives the good critical point in there.
Wow, okay, that's really
so this is the prototype that they make. So
that's really cool.
So
that's really cool.
So the FPGA
would love this. Yeah, Yefta's here. Yefta's our CTO.
Yeah.
He does this. Wow, that's really cool.
Yeah, it's a lot. Yeah. But this one is actually the FPGA is not specifically for mining. So this one is just a normal data centers FPGA that you can buy everywhere. This is the experiments that they did, that the Whitefire did, the guy we call Whitefire. So he ran the Tribus algorithm. The Tribus algorithm is work for Denarius and Frintus coin. That's a small coin, right? So they benchmark the performance. So first use the GeForce 1080 Ti, and it reaches 91 until 100 something megahertz per second, which is very low. But for FPGA, it's 6 to 20 times faster. Like because all the cryptography algorithm, we put everything in the FPGA so that it fits a lot of and how I can give a very low latency in there. Yeah. So this is for the small coin like video. So this one make for combiner excited.
Difference is amazing, man. That's a significant difference.
Exactly. Yeah. Then reconfigurable, right?
Right.
Yeah.
Right.
So if
Do you
one
have
crash,
any-
just make another algorithm.
Right. Do you have like any benchmarks for SHA-256, for example, or Kryptonite, like Monero, or?
No. Sorry, what do you mean?
So did you have any did probably the person who made the benchmark did you?
Oh yeah. I mean, we know the guy. We know
Okay.
Whitefire.
Okay, so did he like make any examples for SHA-256 or probably for Kryptonite, for Monero, for example, or it's just like something that does not make sense to look on?
Hello.
Either could you,
Yeah.
was my question not, probably not there. So how about SHA-256 or like Kryptonite? I don't know if you know Kryptonite's
Oh,
Monero.
Kryptonite.
Right.
Actually, I don't really know.
I see.
Yeah, I don't
I
really
see.
know. Yeah.
Gotcha. Thank you.
Yeah.
This
Yeah.
is
All
a
right.
really cool.
Yeah.
Okay.
That's fine.
Okay.
Yeah, I don't really know. Yeah.
Okay.
Yeah, actually, oh yeah, for how it works and how it's designed, so it's actually just like CPU and GPU mining. So just like transaction verification, right? We get the right hash, uh, and then we get the reward or something like that. But because FPGA, we just replace the CPU or GPU instead of GPU, we replace with the FPGA for the hashing process. So we report the hash back to the CPU. So after get the hash CPU and it report back to the from FPGA to the CPU and CPU to pool,
Okay.
and the CPU will confirm whether you get the right hash or not. So the design process is normally we just translate the C or C++ from CPU-based mining or GPU-based mining from OpenCL or CUDA, or there are white paper in there, and then we just translate into the Verilog. But it's not just translate because we do need to do optimization. That's the hardest part,
Okay.
right? So we need to, because we want to reach the very high hash rate as high as possible. Yeah. So comparison. So actually here, this is a better comparison of the between ASIC GPU and FPGA. And actually for the, this is for the customer perspective. So ASIC and GPU right now normally more user friendly because just like run the FPGA and it has the miners. So there are two things different. So they need to be configure and to concern about the CPU side and also concern about the FPGA side because there are no mining like 100% with FPGA. So FPGA just do the hashing core in there. So user normally need to think both of them, right? And also for the hash rate power and for ASIC, it's very high, uh, comes with a very high hash rate and also low power. But FPGA is also like that, but not as efficient as ASIC, right? But GPU is much lower than that.
Okay.
But unfortunately for the ASIC, right, because it just can do mining a specific coin, so it's not adaptive. But the GPU and FPGA is more reconfigurable. But here, on the right side, actually the GPU has more algorithm that can be mined with GPU than FPGA or than ASIC.
Okay.
Because there are some coins that has FPGA and ASIC resistance. For example, the core, like the core algorithm in the core will be changed every time frequently. So that makes the FPGA resistance that we cannot mine that with FPGA.
Wow. Okay.
Wow.
Okay.
Yeah.
So,
For
right. So,
yeah.
wow. Okay. So there has been a lot of things in the crypto space where a designer of a consensus algorithm might say like, hey, let me, or a hashing algorithm might say, hey, we try to make our algorithm so that I forgot what's it called. So it discourages ASIC miners to go and get all of the mining power. So I guess designs as a cryptocurrency owner, like designer perspective, having at least FPGA friendly algorithm or GPU friendly algorithm might be better than having basic, you know.
Yep, right. Because when they design, I'm sure they do the abstraction layer from the behavioral to RTL, and also do the some kind of the place and route, right? After that, they optimize that again and put that into the silicon. So every digital chip process is when they do the prototyping, always to go through the FPGA stage before they design and manufacture the chip
I
and
see.
yeah.
I see. So it always goes through the FPGA
Always.
phase where then
Yeah.
after at a certain economic incentive, they were just like, let's go ASIC. Is that correct?
Yeah, it's
Okay.
correct. So that's actually a lot of like a big decision when we move from the like a reconfigurable base algorithm to the ASIC. That's a very bold move actually. That's very high risk and bold move. A lot of investment in there, right? Because like you cannot use that one. So you need to really need to certain that algorithm will be very profitable with this ASIC.
Right.
Otherwise, your ASIC will be a junk, will be a rubbish.
I heard it's like $20 million to just like get the design and everything and all the fab going on for an ASIC one liner. So that's it's really expensive.
Yeah. That's one. And also, actually, if you want to learn something for FPGA,
That is really cool.
start is
I see one ad.
yeah.
Wow. Okay.
From just go googling FPGA.guide.
Yeah.
So
You're the
I
man.
think that's
That
all.
must be really good. That's really cool.
That's interesting.
That's really
Thank you.
I got several questions. One by one, or
Oh yeah,
Go ahead.
one by one. I think one by one.
okay.
Yeah.
The first one is when you say limited register, register trade-off. I can think that FPGA has limited register, right?
Of course, yeah.
How many is limited? I mean,
Depend on the chips that we use.
depends on the chip.
It depends on the chips that we use. So, for example, here, the chip that we use is Kintex series. Kintex series normally used for the data centers. Okay, so its chips, if you buy in retail, it's cost $100, but if you buy in large scale, maybe $80, something like that. Yeah. So that one have 100K of loot. Sorry, 200K of loot and 400K of register.
Okay, 200.
Yeah.
200K is a lot.
That's a lot.
Yeah.
I mean,
But
comparing to GPU, yeah.
Yeah, that's a lot. That's a lot. Wow. Okay. Huh.
And nobody else asking?
Go ahead.
Because so many questions in my head.
Shoot
Um,
away.
okay. So can I plug an HBM memory into FPGA?
Yeah, sure. Yeah,
Oh.
there's a HBM memory in FPGA, but yeah, actually, there's like a couple months ago, we want to design the SBM memory because we want to mining like Ethereum, but it's turned out in terms of the cost effective, it's not cost effective at all.
I see, not
Yeah.
cost effective. Okay.
Yeah,
HBM is high bandwidth memory.
memory. Yeah.
What about the lowest latency memory we can plug into FPGA? Is it dynamic RAM or static RAM or
A static
I don't
RAM.
know.
I think
Static RAM. Okay.
Yeah, you can use a static RAM. Actually, there are some of the FPGA has a different features, right? Like the registers that inside the FPGA normally we don't use to store the data. Like if we store like the data, like for example we do the
Oh, barusan ada nggak dengar?
hello. Hello.
No, sorry. There was a guy.
Yeah.
Okay, go ahead.
Yeah. When you guys do the image processing and stuff, right? You start something into the buffer before you take it back. So normally, that's a lot of A lot of memory that you need for the image processing. That one we use the RAM, built-in embedded memory in there to store the image. Yeah.
Okay.
I see.
Okay. So I remember when I was still doing my PhD, and I was doing it in deep learning, and a lot of deep learning algorithms uses GPUs, right? So the reason why deep learning 2014 was a big hit was because of an image competition, which was like pushed by GPU. Parallel algorithms implemented in GPUs. Right now, everyone's going into like FPGAs into it, and I believe like there's people designing. I think Nirvana Systems from Intel designing also algorithms that could be implemented in FPGAs and ASICs too, which is I like I guess it's really a cool part about high performance computing. Yeah. I guess Krishna, go ahead. I'm sorry.
Well,
you can turn it
well, I have a lot of questions. I mean, I used to code GPU code, right? And I do trigonometric computation there. And what I found out in GPU, that trigonometric computation is memory bound computation, right?
Memory bound. Yeah.
Yes. What about in FPGA? Is it still memory bound? I mean, register using or what?
Yeah, because that's a lot of floating point. Right?
Yes.
There's a lot of floating point. Yeah.
See,
Normally, if there's like that, yeah, HBM is the good solution.
Yes, because it's
HBM.
high bandwidth.
Yeah, high bandwidth.
Okay.
I see.
Okay. Huh. I could imagine. So maybe Yefta, do you want to like or Hassani maybe? Hassani is designing a blockchain right now, maybe a private blockchain. Maybe he wants to like add something.
Yes. Hi guys.
Hi.
My question is about you can actually do hashing in one clock, but this clock is the combination of all the stages that you do. Is that correct?
No.
Okay.
No, because so this clock is the worst case delay.
Okay.
Of the stage. So
that answers my question, because you cannot actually do a hashing in one stage.
Yeah.
Okay.
We can.
Another question. Do you use the clock as your entropy?
What is the entropy?
Entropy is the random. Oh, okay. So before that, is your hashing we call that is your hashing normalized?
I like
Is your hashing kind of perfect? Do you consider collisions?
Oh.
Do you consider
hash collision?
yes, in your hashing algorithm? Because it is practically, unless you define your own clock,
Right.
and
Yeah.
it is almost impossible.
So this is asynchronous. This is synchronous.
Okay.
So the data that comes from the pool, and the CPU will grab the data and pass through the data to the FPGA. So in our case, we use the UART, and then there's a synchronous UART, and after that, the FPGA has the buffer in there and do the hashing. After that, we'll give the output in the and UART back to the CPU, and the data will, the hashing data will go back to the pool for the confirmation.
Okay.
All
So
this kind of-
how do you generate randomness?
So randomness. I believe. Discussion about FPGA. You could like get sources of randomness which are different sources, right? It's not Radhian's like presentation isn't like hashing specific, right? Or like crypto specific. You could like generate randomness from, I don't know. If you could go forward, correct me if I'm wrong, Radhian, you could like go to, you could implement a Mersenne twister there too, but you could get source of randomness from the bus, for example, right? You could read, for example, I know, maybe bit.
So from noise, from
random.
Okay, from noise. That makes sense.
Right. So
because hashing implies you need to have some sort of randomness from from entropy somewhere.
Right. Either a randoms or pseudo-random algorithm, right? So
yes. So Radhian, in your hashing method, do you introduce noise from outside or from other source, or it is within your algorithm inside your FPGA?
Actually, I think outside.
Okay.
So the CPU will like give the randomness.
Sure.
Yeah.
Right. Because I get your mathematical perspective, Hassani, because like generating random numbers is an expensive operation usually. Is that correct?
It is definitely.
I used to have a professor who specializes in that, and it's generating randomness is a very expensive operation.
Okay.
Yeah.
Cool. And also because in crypto it is calculated as in how many hashes per second.
Right.
Have you tested your output hashing algorithm as in it never collides? The product
the amount of probability to collision, right? You just run the algorithm until like how many million it gets collision. Is that what you mean?
Correct. Because it is very dangerous. That's very dangerous.
I think that's a more mathematical question, right? Instead of a hardware question. Correct me if I'm wrong, because like you could technically analyze, or you could do an analytical computation, except maybe you can't prove the bounds, right? Are there hash algorithms that you cannot prove the bounds?
Yeah, but that's the problem. If you want to use FPGA, I know you can by electrical engineering you can verify your design,
right?
But you have to also verify your design in mathematical correctness.
Right.
It doesn't matter. It doesn't make sense. You can
both implies the same, right? If you have
exactly
like mathematical correctness, you would always 100%.
So
for sure.
if you can guess a billion hash and you have a 50% collision, that's trash. That's non-usable.
I get what it is. I get what your point is. Okay, that's really okay. So anyone who would try it on a FPGA might have tried it on a CPU before, right? So
yeah.
Yeah. So is there any, so I guess your question is geared towards, are there any hash algorithms that might be tested on FPGAs that might not be tested on CPUs?
No, never.
Never.
So never. So we always confirm either GPU or CPU first if it
Okay.
works. So we
Okay.
yeah.
So it's a normal.
So we normally
Second question.
Yep.
Okay, so interesting with the FPGA resistant. How can you just briefly explain how to do that? How is it possible the GPU can deduce a problem where FPGA cannot solve?
Nice. I think it's
That's
not that the
interesting.
FPGA cannot solve, but I think the amount of efficiencies are. That's where it becomes the question, right?
Yes, basically.
So what is the question? Sorry.
How can you briefly explain how can a GPU can solve something that FPGA cannot?
So here, normally there's spec that cost spec, right? Because like for the deep learning or something like that, that needs a very floating point, like a floating point, and that's a floating or trigonometric algorithm. That one actually, if we use the CPU, if we use the FPGA, it needs a high scale, like a lot of load, lot of LUTs, a lot of registers, a lot of, or we need to touch a HBM. But and eventually, in the cost wise, FPGA is not that efficient anymore. It's
Okay.
GPU, yeah.
So it's more economic instead of
economic, yeah.
solvability.
Yeah,
I see.
Because once you have gates, you can solve anything.
Right.
yeah, it's a little more economic because the price is quite different.
Right.
Okay,
Yeah.
sure.
Right.
And also the key to FPGA is also the clock. Okay, the clock is actually the $1 million question. What's the fastest current available FPGA?
What's the fastest current ever?
Yes,
So,
the fastest
Clock, right?
the CPU, the clock.
so currently, as I know, but I haven't tested in real life, right? Is until 3 gigs.
3 gigahertz. Okay, that's all right.
Yeah.
That's a lot.
Yeah. But I never test in real life. So
Okay, that's going to be very expensive.
yep. Yeah. So in my real life experiment is 750 mega.
700. Okay, that's
Yeah.
all.
Okay. Yeah. Maybe is your blockchain algorithm mining based or not, Hassan?
Sorry, again?
Is
I couldn't get.
Is your new private blockchain algorithm mining? Like, is it a hash based algorithm or?
Nah, I don't actually do blockchain. I'm just doing the distributed ledger.
I see.
It has some blockchain, as in
I see.
the tree is connected.
Right.
It is hash, but it's very simple hash, and it is calculated quite. I haven't tested, but it's supposedly quite effectively done in the CPU because of it just using simple AES hashing. So
I see.
it's very cheap.
Okay. What's if I may know, what's a hashing algorithm, or is it still secret?
No. It's just standard cryptography.
Okay.
Yes.
Okay. Cool. That's really cool. That's really cool. Yeah, I remember there was like several operations in deep learning that back then I was working at Mila, right? So Mila was where Theano got invented, and Theano got integrated as TensorFlow right now. I guess everyone knows TensorFlow. And then, as Radhian mentioned about a lot of floating point operations, and now in CPUs there's AVX operations, right? AVX.
AVX 500.
Yeah, there's like SIMD operations in CPUs. My question is that is there a point where actually the CPU, because I've seen now like the CPUs put a lot of SIMD operations there, right? So is there a point where these CPU manufacturers could catch up with, you know, at least being on par in terms of what you mentioned, Radhian, about the moderate to what, like the efficiency for parallelism? Because like we all know like parallelism is like the way forward, right?
Yeah, the way forward.
Right.
So here, so with the CPU, so do you mean the performance wise or price wise?
So either both. What are like right?
Okay, so yeah, so right now in terms of make the density of transistor become higher is a lot of job, a lot of like R&D, and it's pretty hard. So normally people just do in the circuit level design and also the like parallelism design and that, yeah. So mostly I think the innovation will be in the what the higher abstraction, like the
I see.
how it parallel.
How parallel?
Yeah,
I see.
yeah.
I see.
I think so because from the graph that I showed previously, right? So like the number of parallelism is much more higher than how the density of transistor increase.
I see.
Yeah.
I see. Okay. That's really clear. One probably just like one more question for myself, maybe others would ask is, since for our application, your application is more monad is crypto mining operation, right? For ourselves, I remember we were talking about how maybe you mentioned about maybe using FPGAs for HFT or like exchanges like us is overkill. Right now, sometimes in the past I don't know how to use it. You know, my knowledge in FPGA is almost zero. And then now after your explanation, now I really get how it's you know, how the synthesizers work and all sorts of stuff like that. How like because a lot of our matching algorithms aren't actually parallelized. I believe Kresna might get, you know, understand this too, and the others. But so for trading applications, I'm still seeing that the applications in other than the matching algorithms might really be used for FPGAs. I mean, so might use FPGAs, like for example. But the hardest part, I believe, is, you know, switching host, like from the FPGA. You know, I still have no idea how I could process, for example, a simple UDP packet, right? From the FPGA and deconstruct that for, you know, for orders, for example. It's more of how do you actually, you know, how do you actually connect the host with the FPGA and do it also in a fast way, because that latency also matters, right? Sorry, was I disconnected? Radhian, there?
I can hear you.
Was my question a little bit like? I was like, was I muted, or did you get my question? Or? Is Hassani, could you hear me?
Yeah, I got your question.
Okay.
It's Radhian might be disconnected or something.
Yeah, maybe Radhian is disconnected. Oh yeah. Anyways, this was like probably longer than what Radhian expected too. So, is everyone hearing me well, or Kresna?
Yeah, I can hear it, but in my place it's very noisy right now.
It's okay. It's okay. Maybe Radhian is here. Did you get it? Let me go. He seems that he says like he said in the chat, "Hey, can you hear me?" Oh yeah, sometimes Zoom is like that. My bad, man. Could you hear us, Radhian? Could you try speaking on the microphone again? Ah, okay. We still can't hear. Okay, try to mute, unmute. I tried muting and unmuting. Oh, okay. Okay. Okay, it seems that it's just we cannot hear you. What's usually you could do is, okay, yeah, that's it. And then mute, back, and mute. How about now? Could you try speaking now to the microphone right there?
Yep.
Right.
I can hear you.
Yeah, I spoke already. Oh, I see. Yeah. Is it just me? So yeah. Okay. I think you were no good. Yeah. I don't think the others heard you, Radhian. Maybe could you connect and disconnect again? It's a Zoom problem. It always happens. I'm sorry, man. Okay, no problem. We'll still be here. No worries. Wow, that was really cool. That was really cool.
I was going to ask about B-tree or sorting algorithm in FPGA.
Wow. Yeah. Okay. Yeah.
Is that possible? Yeah, we'll wait for.
Right. I think it would provide a very fast interface, but the parallelism is just, yeah, it's just amazing. Oh, I could imagine that.
It's really interesting for me too, because from our perspective, the way if we truly want to quit performance is to actually using the cache. So as long as we don't invalidate L1, L2, L3, we have a very fast performance. But that's very hard with the introduction of operating system schedulers.
Right.
Okay, so if we eliminate those schedulers, if we have a real-time kernel, then we can have a guarantee. But then again, we have to make sure that our registers and our application pointers, function pointers, stays in the L1 cache.
Yeah, full control.
Exactly. But then again, it still costs a lot of wattage.
Right.
In CPU. That's the problem with CPU, that the FPGA totally bypasses that. No OS, no operating system, zero latency. No, I mean, very small latency.
Yeah, no zero latency.
Yes, of course. And also, but still at the lower clock. Okay. By the way, my guess from mathematical point of view, you can actually do any sort of algorithm, Krishna.
What do you mean you can always do? Sorry, so
yeah, so sorting, searching, it's not easy, but they can do it. The problem it will be the stacks and
yes, that's true.
the registers.
Yeah, that's right.
Right.
So yeah, I was thinking maybe matching engine can be I mean, like I can create something like embedded system like where I have full control of the register and memory.
Right, that's possible too. Right.
because B3 hash map is, I think, it's impossible in FPGA, but I need Radhian to answer that.
Yes, please.
Right. Yes, please. Radhian is here, and I think could you try again, Radhian? Maybe if your mic works, or yeah, we still. Hello. No, yeah, we can't hear you, man. Could anyone also confirm that it's not on my part only? Or?
Yeah, I cannot hear him.
Okay. Should maybe check your mic. Oh, this is on. Yeah. Management. More. Okay. Shoot. Okay. What's the best way forward here?
That's too bad.
Yeah.
I think Radhian can chat, then Dendi.
Okay. that would be cool. I'll do that. I'll happily do that. You can
because
chat as
because I need the answer badly.
This is really interesting. I'll just go forward for the whole night. Maybe not the whole night, but
yeah, I really need the answer.
Yeah. Okay, so I guess everyone could ask a question and maybe. Okay, thanks, man. So go ahead, shoot some questions.
Yeah, about B3 or sorting algorithm. Can FPGA do that? I mean, for that, yeah. Radhian? Oh, I think he is writing something.
Right. Aha. We could try that again. I think we could hear. We just was able to hear you a bit, Radhian. Yeah.
Hello.
Okay.
We can hear you. We can hear you. So
Hello?
yeah.
Can you hear me?
Houston, we got connection.
Yes. We can hear you.
Oh, okay, cool. I just plug on and plug off the headset. I don't know why. Okay.
That's silly. Okay. My question is about sorting algorithm.
Mm-hmm.
Is it possible we implement sorting algorithm in FPGA?
Oh. Sorting
like
algorithm.
List sorting, array sorting. Yeah.
So
is it normal?
That's quite memory expensive, right?
Yeah. That's right.
Yeah. When yeah, it can do that, but it's not a common practice. It's
not common. Okay.
Yeah, it's because if it's memory expensive, or normally we use FPGA for the parallelism, for the computational cost. If we need a high latency, if it's high latency, we need to reduce that. So we use FPGA. But for the, it's possible, but it's not common because normally the registers might not enough to cover all of that. Or if we add more registers, means more more sophisticated chips, which means more costly, or more we put like HBM memory in there, or like something like that. Means,
exactly. I was thinking that if you want to sort a million by a million or a billion by
I
mean, it's just like someone would just why use an FPGA?
Yeah. Okay.
I could imagine someone just why? But that would be interesting to try.
I asked that because a GPU is also limited register, right? Only 32 kilobytes register, but it has fast memory, right?
I remember something now. There's a parallel algorithm for sorting. I remember this now. I remember this in my algorithmic complexity class. There was a parallel.
Something's GitHub, yeah. Huh?
Yeah, so you could actually do parallel sort on each core, and yeah, I'll try that. I'll try that on Tinder, and then maybe we should try that. So a little bit of the context, Radhian. Maybe it's definitely something that not in the crypto mining. So maybe you don't sort a lot, but like in what we do, Kresna and I and Yefta and Susena and Ogi, we do a lot of sorting, because like you need to sort the orders based on the lowest to the highest, and then for the ask to the highest to the lowest, or vice versa. So it's a lot of sorting. Every single time an order is coming in place, we need to sort or insert it in the right position. So that's why being able to sort efficiently is one of the holy grail of what we do. I guess
Like,
the $1 million question is,
yes, the
how do we
$1 billion.
sort efficiently?
Maybe $1 billion question.
Yeah, maybe $1 billion question. Exactly. Yeah.
Dandy, you should readdress your question back.
Oh, I should address my
GDP.
question.
Yes, please, because I/O is important.
Okay, so my question back then was, what was my question? Okay, so
FPGA for
Matching.
fixed protocol, maybe.
oh, right. So okay. So we all use, I believe from your presentation, like we all use it, these hardware accelerators for the sake of latency, right? We want to compute something very, very efficient, very, very fast. So when I remember when I was talking to you in past fest, right, and you were like, the enthusiasm on about like explaining on a piece of paper. I remember that day, and you're mentioning about at the end of the conversation. I remember we were talking about how do you actually, you've done the computation on the FPGA, right? Now you want to pull it back, and how bad is latency when you send back the result of the computation from the FPGA in bit streams? Correct me if I'm wrong. It's going to be in bit stream. Or is it going to be different?
Oh, so the bit stream is just how we program the FPGA. Like, oh, this FPGA become Intel Core i5, for example. So we put the bit stream in there, but the data, it's different thing. That's the I/O. So now our FPGAs already becomes Intel i5 because of that bit stream. So the bit stream is just stored in the flash memory inside the FPGA in the EPROM. So the LUT will read that EPROM and it becomes the logic gate, and the logic gate becomes the Intel i5.
Okay, so from transferring between the FPGA to the Intel i5, how long does it take?
It's okay. So there's two bottleneck. So it's really depend on the what I/O modules that you use, and also what the I/O protocol that you use. Do you want to use PCIe or USB or UART or XC or it's really depend on that.
Okay.
Oh, the bottleneck is the bus, right?
Yeah, the bus. Yeah.
Okay.
Yeah. So there's another bottleneck. Yeah.
Okay, so that's a different optimizing perspective.
Yeah.
Radhian, in your prototype, how do you connect from CPU to your FPGA?
Oh, so here there's two prototype here. So for the first hardware, VCU 1525, so that use PCIe like a GPU.
Okay.
Yeah. So but for the another prototype, we use UART because we use BeagleBone, if you know. BeagleBone is like Raspberry Pi. So we use the embedded computer. So
it's serial.
It's serial. Yeah, so it's
okay.
serial. Yeah.
I see.
That's wicked stuff.
Wicked stuff.
That's wicked stuff, man. That's wicked stuff. Yefta, who knows a lot about crypto mining, I believe. Want to shoot a question, man? Or
So or maybe here, if you guys using a lot of like, you are mentioning about the match process.
Right.
What is the match process?
Right.
Match process. It's really simple, but I think Dandy should explain it.
Okay. So do you want me or do you want yourself to explain, Krishna?
Please, Dandy.
Okay. The match process is really, I could say it's maybe simple. So an order comes in, right? An order comes in. Maybe I should share my screen or let me. So okay. So matching algorithm. Match algorithm view. So imagine an order comes in, right? So in a market, there's always a buyer and a seller. The main problem in what we are as an exchange is to efficiently match a buyer and a seller. Say Kresna wants to buy, let's talk about Bitcoin since we're all in crypto, right? Yeah. So we want to buy one Bitcoin right now. Right now it's 9,300, right?
Yeah.
And something. That's also, so say I want to buy or place a bid, what's in the financial lingo, I want to place a bid for one Bitcoin at 9,200, right? And then Kresna comes and then, hey, I want to sell my Bitcoin at 9,400. In that case, because 9,200 and 9,400 don't overlap, means that the ask or the bids are not, the bid isn't higher than the ask, then there's no match. But for example, Aditya Suseno comes in and says, hey, you know what, I wanted to, sell at 9,200, right? And then literally simply what, my Bitcoin, I can get one Bitcoin from Aditya Suseno. Basically, then what happens at the back end is Aditya Suseno sends him or, us as an exchange, takes Aditya Suseno's one Bitcoin and transfer it to me. And the exchange takes my 9,200 and places it in Aditya Suseno's account. A very simple thing. But imagine if normally there's like millions of orders, not like millions of dollars of orders, but millions of orders in the queue that are, for example, you can imagine if the price tick is $1, it's 9,300, 9,299, 9,398 until like say probably not zero, but probably like 9,000, right? And then there's billions of those in memory. So right now for our exchange, we do all of our operations in Redis or MemSQL, which is all in memory. One particular, very interesting thing is that in an exchange, when you send the order when you receive confirmation, it's not just a matching algorithm, right? It's also receiving the order from the gateway, clearing or swapping, as I told you, moving one BTC from Aditya Suseno's account to my account, and then at the end display or send what we call a market data request, market data back to the client, and that is called a round trip. One round trip for the biggest exchanges, which all uses FPGAs end to end, is 1 microsecond. So imagine if a client sends an order, it receives at the end of at the beginning of the gateway that uses FPGA, processes that TCP packet, changes that into binary format, dumps it to the matching engine, and then the matching engine also uses FPGAs. As Kresna mentioned, sorts all that, million by million.
Yeah.
Also, right? Go ahead. Sorry, were you asking about something?
how the FPGA, I mean, for 1 microsecond things, but he need to do the matching process, right?
Yeah,
And when the matching process, it's interact with the memory, I believe.
right.
Yeah, and
I remember you mentioning about, Delhi, like, I remember you telling me back then, like, like 1 microsecond is very, very slow. Even for FPGAs, you can do nanoseconds for that, right?
yeah, if just inside the FPGA, yes.
Exactly. So I
Yeah.
called up my friend and he said, like, matching takes like nanoseconds, man. The whole problem is the round trip.
Yeah, that's correct. That's
Right.
correct.
Yeah.
So we turned on and we thought later on, maybe in a year, right? So right now we're writing this whole thing first, but going forward, we want literally every single engines of ours written in FPGAs, and that's how that's how prevalent, I guess, FPGAs is used in the industry. Because like it's not only for sorting, right? It's used for clearing also, and also for the gateways.
Yeah, most of the bottlenecks is in the network. Yeah,
IO, exactly,
in the I/O. Yeah,
exactly.
and I can search in the internet. Many vendor is supplying FPGA for fixed protocol and fast protocol.
Yeah. So
That's common. Yeah.
I remember last week I was having a conversation with a Ukrainian firm who has an office also in Chicago. They do have they sell those kind of things. So they told me they do FPGA level fix formats. So for Radhian, maybe who doesn't know maybe about fix is some sort of JSON format to encode what's an order. So if you want to buy or sell, there's a specific format that you need to follow, and it's been designed by these guys in '86 or like '92 or something. That's yeah. So it uses a format called fix, and turns out they do the transcription all in FPGA. So, yeah. So yeah, did that answer your question, Radhian, or do you,
Yeah.
right?
Yeah, round trip, and actually
Mhm.
maybe everything like the decoding from the UDP, how the like the payload will be will be reconstructed
Exactly.
into it can done in FPGA, but I think the most of the bottleneck is the interaction between memory.
Exactly.
Yeah.
So there's my question on this class on Radiant. So imagine the computation is on FPGA, right? So suddenly suddenly the power supply just got shut down. Is everything lost or?
Uh, yeah, sorry
It,
for
right. So if there's a problem with the system and with the FPGA system, is everything lost or?
oh yeah
Okay.
yeah, that's right. That's
It's
right.
lost.
Yeah.
Okay. Wow. Okay. So how do you prevent that? You must have like experience, and how do you must have saved the data somewhere in the middle of a computation, and you just let it go.
Oh, we normally, if we want to save, so we put that into the like RAM, like
Okay.
a embedded RAM.
Okay.
Yeah. So if we want to do that, so
Uh-huh.
in the embedded RAM normally can store the data, uh, even though I mean it's more robust in there.
Right. Right.
Yeah, but still here, if the power turns off, everything lost.
Okay.
Yeah. So normally we add so in the current system we have the flash memory outside, another flash memory,
You
right?
have another flash memory.
Yeah, another flash memory outside.
Okay.
So we put the data into that flash memory.
Okay.
Yeah.
Okay. Okay. That's okay. That's really cool. Okay. So Crash, I guess Cressler, go ahead.
No.
Okay. Okay.
So what's the current bandwidth of the PCIe from the general purpose CPU to your FPGA?
Mm. Ah, actually, I don't really remember because it was. I mean, for now we use UART. Like for 1 year we use the. I mean, we already left the prototype that using PCIe.
Okay.
Because I mean, for the hardware perspective, we need to invest more in FPGA, not in the CPU side.
Okay.
So yeah. So actually, I don't really remember.
I
So
can answer that.
what's the split? What's the split on the serial?
Oh, 9 to 1 600 baud rate.
Okay,
UART.
both.
Yeah,
Well, yeah, that's pretty slow.
yeah, yeah.
Oh, it's wait. What's the board?
9,600.
No, 9 to 1 600.
Oh,
Yeah,
9 to okay.
yeah, 9 to 1, not 9 600. 9 to 1 600. Yeah,
Oh, that's fast.
yeah.
Yeah,
For UART perspective, it's fast. For
yeah,
UART.
that's right.
It's like 15 years ago modem.
Uh,
Yeah, that's 1 megabit, almost 1 megabit.
mm,
That's 1 megabit.
yeah,
Okay.
But no, that actually incorrect. Baud is 11 bit per second, right?
One baud is 11 bit. So
Yes,
11 bit.
with
yeah.
corrections.
Sorry. Yeah,
Yes,
sorry.
with correction.
one baud is 11 bits. So 9 2 what? 9 2 to 9 2 2 9 2 9 4 2 600. So 1 2, so 10 million bits. First one. That is my calculation wrong?
Yeah, 10 megabits.
10 megabits.
About 10 megabit, but
Yeah, 10
the
megabits.
the data is 8 bit.
The
Yeah,
data is
the
8
payload is 8 bit. Yeah.
Yeah, the payload is 8 bit.
8 bits. So divide that by 8. So 1.2 bytes.
Yeah, while in PCI Express 3, we can achieve 8 gigabytes per second.
Oh, wait. Oh, wait. Is that something that's different? No, right? But as I'm seeing the ones that you shared on the on your slide image, the kids do have PCI Express. But
Yeah.
that's okay.
Yeah, that's the prototype, the very first prototype.
Okay.
Yeah,
The prototype.
the prototype. Actually, the current salt board is no longer use PCIe, just UART, because the majority of the hardware cost is mostly in the hashing board, in the FPGA board. So because if PCIe, we need to use a regular motherboard, which is quite expensive and not compact. So
Okay.
Yeah, big.
Okay. Cool. I guess that's it for me. Krishna, Hassani, or Yefta, Augie, do you have any questions? No. Okay. Demi. Okay, so Demi Dimas, hey, welcome to the OX04, OX03 Cypherpunks Dev Conference. Welcome. It's a conference that's done like every month on the first Friday. And first of all, I want to apologize to Ogi because like he filled out the OX02, and I said in the beginning I forgot about that. I did not. I guess welcome for Dimas and Demi. This is like firm agnostic, right? So anyone from crypto to deep learning, anyone who wants to like just chip in for the sake of science and knowledge, feel free to yeah, hey, like Dandy, I want to like present about this. Maybe Hassani, what do you think about next Cypherpunks conference? Do you want to fill up, man?
I'm good, Mike.
Okay. So yeah, we regularly do this, and don't hesitate to reach out. I guess that was a really cool presentation, Radhian. I learned a lot about FPGAs. Thank you so much for agreeing to explain us, patiently, and also answering all of our questions regarding to FPGAs. We really had a lot of fun. I guess. Well, do you mind if you put your slides or share it with me later on so I could post
Oh
it
yeah,
somewhere?
sure.
Cool.
Okay.
Thank you so much.
All right.
Yep, I guess that will be it from OX03. I can't wait for OX04. There's a guy called Songkeng Maldini who's going to explain a bit on the fixed protocol, and he wrote a fixed parser in C++. So anyone who's interested might join like next month too. So yeah. All right, guys. Thank you so much for your time. Thank you so much, Radhian.
Thank you.
Thank you.
Really
so much
cool,
for-
Radhian.
Coming.
Thank you, Denny.
Thank you, Susanna.
Thank you, guys.
Thank you, Asani.
Thank you, everyone.
Thank you, Budiman.
All right.
Thank you,
Thank you.
Radhian.